So I thought I would present to you something I didn't have time to present yesterday. This is not finished, there's no paper, this is work in progress, this is what keeps me up at night. Don't scoop me, I haven't published this anywhere. So you see, yesterday at the end of the talk, we left after having been able to calculate GCD with a fairly good accuracy. So we showed that transformer can learn relatively complex arithmetic function, more complex than multiplication or something like that. You need to work for it by maybe adjusting the training distribution and all that. And you can usually understand what the model is doing just by looking at the model prediction. So it's an interesting approach to interpretability, because usually when people want to do interpretability, they look at the weights. The problem is that even in a very small model, you have hundreds of thousands, if not millions of weights. So how do you make sense of a million of stuff, most of them random? It's extremely difficult. Looking at model prediction provides an avenue for explanation of a simpler nature. Okay, but this was a fairly simple case. This was a classification problem mostly, because you just have a small number of possible outcomes. GCD 1 to 10, account for 99% of all examples, or all the GCDs you will see in your training set. So the task of the model there is to take the inputs, classify them into a small number of classes corresponding to single outcomes, and then assigning an outcome to every class. What if we worked on a much harder problem? So I want to talk about the infamous Collatz problem, which I will show is a regression problem. So, it's typical in machine learning to distinguish between pattern recognition or classification, where you have just a few, you want to distinguish, two kind of, or three or n kinds of elements, and regression when you want to estimate a function, and admittedly, regression is a much more difficult thing. So, Collatz, you probably know of the Collatz sequence. It's this funny mathematical object. You take an integer, a positive integer. If it's odd, you multiply it by 3 and add 1. And if it's even, you divide by 2. And then you get a sequence, of numbers, of integers that go one after the other. So the Collatz sequence, there's a very famous conjecture that says that all sequences end up with a subloop, which is 1, 4, 2, 1, 1, 4, 2, 1, and everybody. So nobody has been able to prove that. People are advised not to work on it, except if you're Terran star, but apart from that, you shouldn't work on it because it's too difficult. Erdos said that mathematics is not ready for this, etc. So I'm not interested in the Collatz conjecture. I'm interested in the sequence. And the sequence has an amusing property. Suppose you start with an odd number of the form 2 to the k m minus 1, where m is odd. So k is the largest power of 2 that is a number of zeros at the end of the binary representation of m plus 1, or the number of ones at the end of the binary representation of the number, right? If you have such a number, after exactly 2k Collatz steps, the number 2 to the k m minus 1 is transformed into 3 to the k m minus 1, which is an even number because m is odd. And then you have a number of k prime, it depends on m, obviously, down steps, okay? So I'm defining on the Collatz sequence something I called long Collatz steps, which are these transforms. I start with an odd number. I multiply it by 3n, I do n to 3n plus 1, then divided by 2 k times, and then I divide k prime times by 2. Okay, so this is just a complicated arithmetic function, which is pretty much a regression function. If you look at the 50 million odd integer between 1 and 100 million, you got about 25.2 million values of this function, of this Collatz long successor or long step. So the question is, compared to the GCD, it's way more complicated because the operation is itself complicated, and because it's not a many-to-one mapping or many-to-few mapping, but it's close to a one-to-one mapping. So we're learning a function here. So could transformers learn this? So, it's always the same thing. You get transformers. You generate odd numbers between 1 and 10 to the 12, so that you have lots of them and you'll never see the same twice. You sample them uniformly, you use small transformer, and you will encode them in 2 different bases. So I try all the bases between 2 and 57, and the goal is that you have a sequence which is your initial number, and then you have the long collat successor, you know, the 3m plus 1, etc. And you want to see if, using the first, you can predict the second. And much to my surprise, there are 2 bases, base 24 and base 38, where the model achieves 99.8% accuracy, which means if I test on 100,000 examples, there's only 250 errors in those 2 bases after, you know, a couple of hours training the model, which means the model is able to learn this pretty complicated regression function. So this is one of the constant surprise with transformers in arithmetic, is that some functions that look very easy, like multiplication, long integer multiplication, are very hard to learn, and functions that look much harder, like this one, seem very easy to learn if you have the right base. So the first learning is that, okay, you can learn this with very, very good accuracy, provided you have a base that is basically a multiple of 16 or a multiple of 12. And it's not completely surprising because, you know, base 2 and base 3 are, 2 and 3 are featured in the calculation, 3n plus 1 and divided by 2. So it seems logical that, you know, bases that are high powers of 2, maybe multiplied by 3, would be favorable. But still, 99.8 accuracy is really a lot. What's interesting is what happens if you look at all the bases. So I got tons of different bases, and you can see that if you have, so the accuracies vary a lot from base to base. The even base work much better than the odd bases, which is logical. The division by 2 is easy to perform in an even base, very hard to perform in an odd base, you know, if you just have the digits. But what's interesting is that the accuracy varies between 25% for base 3 or 37% for base 11, up to more than 99%. And even base achieve more than 90%, whereas odd base are below 90%. So, you know, the way you encode, just as in the GCD, the way you encode the data has quite a dramatic effect on how you can predict this function. But it goes deeper. This is so it's a very confusing figure. These are all the training curves. So the x-axis is the time, basically how many optimization step I did when learning. The y-axis is the accuracy, so how many of my 100,000, well, what percentage of my 100,000 test values of the collats I have. And what you can see is that you have steps, and the steps are very clear. You know, all the data seen, all the bases seem to end up at the same values and go in steps. And this is much more surprising than what we saw in the GCD, because unrelated bases still have the same steps. So somehow the learning is quantized as in quantum physics. You know, there are fixed values that you achieve. And you can see here, I give you the values, so 22, 33, 34, 50, 54 are at the same place. And then at the bottom, 7, 11, 37, 55 are in the same place, etc., etc. Okay? And throughout training, you know, when you have different steps, the model goes from one step to the next, but the steps are always the same. So this is relatively strange and curious enough to be worth analyzing. What I make of this is that the fact that it's independent of the base suggests that these steps are a property of the problem, not of the representation. You remember, in the GCD, the steps were a property of the base because the steps were achieved because you would learn the divisors of the base. Here, the steps are the same for everyone, so it must be a property of the collats problem or the collat sequence. So, actually, if you look at so you see my curves. My curve correspond to steps. Now, the next element is that you could try to look at what the model correctly predicts and doesn't correctly predict at each step. So what gives the 25, the 37, etc. And what's interesting, if you look at it, is that the model is learning classes of residuals modulo 2 to the p. Or if you prefer, if you encode the input of my model in base 2, all the steps correspond to a specific binary ending. So for base 7, 11, 37, and 55, so the base that achieve 37 accuracy, so that's the second step, you see it here, I could show that all those models predict some input, some residuals with 99 plus accuracy, and the rest with 0 accuracy. There's no middle ground. So they can predict some residuals modulo 2 to the p, and totally, utterly fail on all the others. And actually, when you look at it, these correspond exactly to all the inputs who have a binary ending in 001 or 1101. 1011, excuse me. If you go to the next step, 55% accuracy, so base 5, etc., you still get 001, 1011, but also 1101 and 00111, predicted with more than 99% accuracy, and all the rest is predicted with less than 1% accuracy. So it looks like somehow the model is learning by steps different classes of inputs, so you either predict correctly the class or cannot predict the class, and the classes of input are defined by their binary representation, which is strange if you think of a model in base 27. How does a model encoding the data in base 27 manage to find, the residual modulo 2p of a large number? This I don't know. And actually looking at that, so the question is, how do you learn base 2 in that? But what do those binary ending mean? And for this, you can notice, so I looked at it and you could actually prove a very small theorem on that shows that suppose, so you remember in Malkolat's long sequence, I got 2 loops. I got a loop of 3n plus 1 and divide by 2, which is repeated k times. And then I got a series of division by 2, which are repeated k prime times. It can be shown that for each value of k and k prime, there's a single binary ending sequence. And so the models are learning the number of steps in the 2 loops in order. So the first thing that the models learn are a case where you have 1 up step and 1 down step. Then it learns 2 up steps and 1 down steps, 2 up steps, 2 down steps, or 1 up step, 2 down steps, etc., etc., etc. So practically what seems to happen, and you can prove, I'm moving a bit fast in the interest of time, what you can prove here is that all the models in different base, the difference between the base, correspond to the number of steps. So the way you learn is sequential. You got 2 loops and you learn the small values you learn to iterate in the loop once, twice, 3 times, etc., etc., etc. And you learn the loops in order. And if you're in a more favorable base, you learn more loops than if you have in a less favorable base, in an odd base. Okay? So we are in a case where we can explain the difference between the base by a common learning pattern for all representation, which correspond to the properties of this Collat sequence, and where the models, are learning all that. What's very interesting is that now we've looked at when the models succeed, we can also look at the failures. And there is this long idea in AI that when the models fail, they tend to hallucinate, they confabulate, they invent something totally crazy. And in arithmetic, I keep noticing that it's usually not the case. And here, it's spectacularly not the case. So I look at my best base, 24, 16, 32, I have 250, 260 errors out of 10,000. If I look at these errors, I can notice that all model prediction will be odd numbers, fair enough, But if I look at the errors are very close to the correct solution. And you remember, those are numbers with 10 digits or more than 12 digits in base 10. So they are big numbers. The probability to randomly get very close to the correct value is nil. But almost all those values are less than 1% or very close away. And actually, it's even more interesting if you decode the predicted sequence and decode the correct sequence and compare them. You will notice that they usually are very similar in the sense that more than half the digits in the representation base will be the exact same. And usually the middle digits are wrong. So the model starts predicting, the solution. The first digits are correct, then it becomes wrong for a while, and the last digits are correct. The first digit being correct explains why the numbers are close, and the last digit means that they are in the same, congruence class for powers of the base. So you can see this in the table. You can see that if you look at in base 24, you have 243 errors. On average, you're predicting a sequence of 9 digits, okay, in the test set. But out of those 9 digits, 4.5 on average are correct. So half the model prediction are correct. Which leads me to, an hypothesis on this. It's that obviously the model doesn't invent, doesn't confabulate. But what seems to happen is that the model probably inside the embedding, inside the encoder, the model almost knows the solution. And it's possible that the solution is correct inside the model, just that the decoder has difficulty, extracting it. But in any case, the model is much better than what the initial accuracy suggested. Okay? If you look in odd base, you remember odd base don't function very well. In odd base, most of the error can be attributed, like between 85 and 88% of the errors, can be attributed to a single phenomenon, which I call the power of 2 phenomenon, which is if you look at the model prediction, it is the correct prediction multiplied by a small power of 2, multiplied by 2 or 4 or 8 or 16. So again, the model was right. It calculated all the upward phase of the collapsing, and just failed on the last loop. It didn't manage to divide enough time by 2. And of course, dividing by 2 in base 3 or 27 is a bit difficult because you cannot just look at the digits and change them. It's more complicated. But what's very interesting is that you can see here that even in the base where you don't succeed, most of the errors characterize situations where the model almost got the correct solution and seem to have a problem, maybe at decoding or maybe at the end of the encoding or something like that. So when you look at the final results in an odd base, you can see that the model, so just like the model successes followed some kind of hierarchy, you're learning higher and higher versions of the values of the loops. You can see that the failures also have a hierarchy. You have easy failures where you predict just next to the value. You have the power of 2 errors for the odd base. And then you have cases, even when you're not very close, you can see that you are a case where the value is almost 3/2 or 2/3 of. It's usually powers of 2 on powers of 3 or the other way around. So the predicted value are always a power of 2 on power of 3 factor off from the correct value. And the more complicated the question is in terms of k and k prime, in terms of the lengths of the loop, the more difficulty the model might have. So what I'm trying to say here is that it's very interesting because what this suggests is that, this idea that models or transformers are very bad at mathematics and arithmetic is when you try to look in detail for a specific problem at what the model does, it doesn't seem that true. It seems that the model knows a lot more than what you see when you look at the accuracy. The model learns patterns which are proper to the mathematical problem you get. The model sometimes has difficulty decoding the solution, but the internal representation suggests that most of the problem was solved. The problem obviously learns something that makes mathematical sense. We have a calculation where we have two loops, and clearly the model managed to do the first loop but not the second or something like that. So what I'm trying to say is that the model seems to know more than it can tell, or more than it can decode. And of course, it's a very interesting direction for research. And it's also a very interesting direction for interpretability, because if we can understand how these things happen, how the model managed to calculate base 2. So, you know, the base 2 for how the model managed to classify its input in base 2 or in even base. I tried to train a model to convert from base 27 to base 2. It fails miserably. The model is not able to learn to translate from one base into the other. But in the Collette's case, it manages to learn this value. So yeah, that's what I wanted to say. I've been a bit too long already. So yeah, this is just to strike your attention. Thank you.
Thank you. Are there any questions? I'm coming. I can go.
Oh, thanks for the really interesting talk. I have some question. I mean, yesterday you mentioned that you are using transformers because it's the thing that all the people is using, but I wonder if all these properties and you have shown is something that also like depends on the transformer, the fact that you are using a transformer. I mean, you can also try to use a different architecture or something maybe different, and I don't know if you can conclude the same or...
Yeah, that's a very good point. So historically, I trained transformer because it was fun. But then, you know, when you push that to conferences and you get reviewer and they ask exactly this question. So I've been able to reproduce, not this one, but pretty much all my previous results using LSTM, GRU, so the previous version of the sequential model. So the conclusion there, and I reproduce really the same results with the same accuracies and all that. Sometimes you need a little more data, a little more time. LSTM are slower to train, etc. But it works. So it's not a property of the transformer architecture. It's a property possibly of sequential models. I don't know whether I could get the same with an MLP, but I suspect so. And the reason why I suspect so was, you know, that grokking thing, you know, that thing on modular addition, that there were tons of paper on that. In the beginning, it was done with a transformer. So everybody did grokking on a transformer. And then there was that guy, Andrei Gromov, who got grokking to appear on a very, very simple MLP, so multi-layer perceptron. And everybody accepted the idea. So I suspect, you know, these base calculations are sort of sequence friendly. So it's probably easier to do in a sequential model like the transformer or the LSTM. But I really don't see why you couldn't achieve that in other architectures. Yeah. And clearly LSTM and all that works.
Are there other questions? Okay. Personally, I think I'm missing an important point in the sense that when you show the accuracy of transformers, okay, this is an out-of-sample error, right? But how is it dependent on the dimension of the training set?
So here, the training set, I'm almost in the infinite case of last time. So
okay.
I got up to 10 to the 12 possible thing, and I run a different element. You know, it's very easy to calculate those guys.
With
so every time
dimensions.
I need training data, I get new guys. I get new tests. So then the accuracy is measured every epoch. So an epoch for me, by my definition, is 300,000 training examples. So I train from 300,000 examples. Okay. Then I roll 100,000 examples and test on it. And then 300,000 more and roll again. So the accuracy I give here are the accuracies at the end of training after like usually 1,000 or 2,000 epochs when nothing seems to move. I cannot guarantee, you know, maybe if I waited longer it would go up.
Okay.
But this was, let's say, the best I could achieve in a couple of days. That would be the good definition. And accuracy is you predict the exact, there's no second price. You know, the accuracy, you have to predict the exact correct value. It's not about it's plus or minus 1 or it's almost good, etc.
Okay, I see. Okay. Okay, well, thank you. If there are no other questions, we can start with the first local speaker.
Yeah.